This function has a name. It was invented by Dirac in early 30s when he formulated quantum mechanics the way you often taught quantum mechanics in modern time. What Dirac delta is morally, but you have to be careful how you define it in various continuum settings. It's really the number of lattice points, because 1 over A is an interval. 1 over A is number of intervals in a unit volume. And that limit is called Dirac delta function. So if you're confused, you can do it numerically. So this is X space, and it has a property that it's 0 unless the argument. And now Dirac delta is worrisome thing in continuum. It's divergent as 1 over A, which is the number of lattice points per unit volume. So we'll always have to be careful that Dirac delta makes sense in a limit. And the way that the mathematics of it works, and also good intuition works, mathematicians call delta a distribution. So it's not a nice function the way we like to think of nice function, because something that's 0 every place and then goes to infinity at a point in this limit. But if you put it inside of an integral, then this Dirac delta function pulls out the value of integrand at its 0. So as operation, it's very well defined. And you think of it as a limit of, a peaked function whose integral is 1 and arbitrarily narrow. So that makes sense, and it works fairly well. Still, you have to be careful.
I guess it's like an ordinary probability distribution that is like 0 at every point. Like there's no probability of getting any result when you make a measurement except for that value.
The way I personally always think of delta functions, in discrete setting is what I explained before. It's an average over all possible directions in a complex plane. So it's either 0 or 1, properly defined. So in discrete setting, it's very easy to understand. Now in continuous setting, and that's why I gave you problem sets with Gaussian this week. I think of it as a Gaussian distribution correctly normalized, meaning that the weight when I integrate over the Gaussian is 1. So, you divide by square root of 2 pi just to make sure the Gaussian integral is 1. That integral depends on parameter, which is the width of the Gaussian or its variance. And I think always of delta function as a limit of variance going to 0, so being arbitrarily peaked. But in practice, it means you're assuming that your function is smooth at the value you're trying to evaluate, centered at the center of delta function. And in that case, works very well. Now, if you have a discontinuous function and you put your delta function right there, then you have to worry, because from the left side and from the right side, you get different answers as you approach that limit. So you have to think twice. But I agree with you. I think of it as probability density. It's the simplest way to visualize it. But for example, when you took contour integrals around the poles, they've also Dirac deltas, even though they were invented in 1820s and 10s, because, if the contour went around the pole, you got 1. And if it didn't go around the pole, you got 0. So, so this was a Dirac function whose index is a contour and the point, is point inside or outside. So that is Dirac because it's continuous. but it has beautiful definition because in complex analysis, it's very rigid and beautiful, and there's no worry about it. You prove the theorem that you're either inside or outside the contour, and that's it. But in real life, you have to be more careful because real functions, real measurements are never holomorphic functions. I keep giving you as reading Roger Penrose's book, and I've taken chapters of it. And I realize no graduate students is going to read it, but now Roger Penrose has a Nobel Prize, so you might think maybe the guy is not totally stupid. He's totally amazing, but he writes a very beautiful chapter about Fourier analysis that looks nothing like what I'm teaching you or nothing what anybody else teaching you. But basically, the basic problem in 1920s is they define functions so rigidly. They define holomorphic and meromorphic functions. They're so rigid that if you specify it on any open interval, then you know it every place because there's unique continuation of that function. Any place once you know it in an open interval, because the analyticity, Riemann-Cauchy, says if you know it precisely on any open neighborhood, you know it every place. Yeah, this is very discouraging because if this is operating in time domain, there is no free will because, if I have a function that I measured for 3 days on planet Earth in my own life, and it describes my life, everything is predetermined because there is unique continuation of this function. So this is beautiful, but this is, what mathematics does to us. Life is not like that, So Fourier was a big problem from them in 1840s when he did Fourier analysis, because suddenly things got a little bit loose. It wasn't the Fourier functions like Dirac delta function is not in a world of functions that holomorphic dynamics accommodates. It just isn't, because if you have zero every place, we prove the theorem, any function that constant, has to be constant any place. So it cannot have a kink. So, Fourier brought us to a much richer world of how to describe world in functions. And that's modern functional analysis. They don't have to be differentiable. They can be all kinds of things. And, so the notion of function is much richer, and Fourier started that. What he did is something that they didn't believe was possible on holomorphic functions. Engineers have to typically use piecewise functions. So they say, I will apply the control for 3 minutes and then I'll turn it off. And then I'll do it for 3 minutes again. So they'll have a sawtooth or a step function or something which will have discontinuities because, you don't want to be twiddling the buttons all the time. It just, burn it for a while, turn it off, burn it for a while again. And he showed that those functions can be approximated by Fourier series extremely well. And, they don't belong to the world of holomorphic functions because they have discontinuities. That's not allowed. But life is full of discontinuities. So, they had a hard time with him, and then they accepted it because engineering works like this. So there is nothing to argue. That's our world. We always define them as positive functions because, our mental picture for physicists is that they're probability functions. Probability functions are always positive, Mm-hmm. Now, because their densities, probabilities usually go from 0 to 1. So if I give you a volume in a space in many dimensions, then I can compute the probability that your measurement is within this volume. And that number will be between 0 and 1 because all other measurements will be outside. But now we define density, we define it by length. Density is probability per unit length. that still has to be positive, but it can go off to arbitrarily high values as I take limits of small volumes. It's always positive. There are representation in terms of X, but really natural representation in terms of Gaussians. As you know, Gaussians are really nice probabilities, and this is a limit of the probability you really understand. The other ones you have to stand on your head like we did when we studied principal values, you know. We had to say, well, I'm approaching it from left and right, and it goes. And the simplest way, in my opinion, is Gaussian to, you know, define delta function correctly for particular application. And basically for physicists, there are two situations. If you do crystals, then the fundamental region is compact. There is a little cell of the crystal which repeats itself. So if you solve the problem in that cell, you solve it every place. And that's why we look at Fourier series and their dual, which is called Brillouin zones, band structure, etc. in quantum mechanics. That's essential to crystalline structures. Or we do it in continuum. We have elastic plates, we have airplane wings, whatever. You know, we have things which don't have crystalline structure. Then we have to use integral transforms. And that's, you know, the two applications.